is currently Chief and Professor, Material Research Center at IISc Bangalore. And he has been a professor in various capacities in various institutions, including IISc, Rensselaer Polytechnic Institute, TU, Hamburg, Germany, amongst others. So his research experience are in the field of nanostructures for clean energy applications, surfaces and interfaces in ceramics and metals, among others. He is also the editor of Journal of Material Science, Springer Nature. So a big round of applause and a warm welcome to you, sir, and over to you now.
Thank you very much. Can you hear me? At the back? Okay, first of all, thanks to the organizers for the invitation. Thanks to Sanil Kumar and other organizers for the opportunity to be here. So what I'm going to do today, I took the liberty of slightly changing, not showing, okay. I took the liberty of slightly changing my topic. It's still going to be an electron microscopy, but my abstract says I'm going to talk on SEM as well as TM, but I thought in 1 hour and a little bit, it's not possible to do that. So what I'm essentially going to do is to talk about state of that transmission electron microscopy. Okay, and that's one of the most like indispensable tools for nanostructured materials, nanomaterials in particular. And therefore, I'll try to tell you in the next hour what electron microscopy can do in terms of characterizing nanostructures, and particularly what we can do actually at the atomic scale. So I think after this very nice talk on Raman by Chandrabas, I think he set the stage quite nicely. The last but one slide that he showed, right, where he showed about mixed states of solids and non-mixed states, and we use a laser beam, you're not going to see the difference at all. Both of them are going to look identical. Okay, which means that sets the motivation that we want actually techniques that can actually show things at a much better resolution, at a much smaller scale, and that is where electron microscopy comes in. Okay, so I think I will start off with this very famous quote, a very famous talk by Richard Feynman. This is the APS meeting sometime in 1959. There's plenty of room at the bottom. I'm sure many of you might have seen this. I think in this talk, he essentially talked about the nanotechnology, but actually 2/3 of the talk almost is about electron microscopy, or a significant part is about electron microscopy. So one of the questions that Feynman raised was, it would be very easy to make analysis of any complicated chemical substance. All we need to know is where all the atoms are. As simple as that, right? If you know where all the atoms are, you know everything about a material. But unfortunately, it turns out that the microscopes that are available for this to happen, unfortunately, was not available at that time. This is the 1950s that we're talking about, right? But it turns out that currently, and so he says that there's no way to make the electron microscopes more powerful. So what is he essentially talking about? Why were the electron microscopes not as powerful so that we could see atoms or things at the very small scale? And so that is a question that we want to ask. I'll start off with something very simple, very basic. So what basically sets the resolution? Okay, what's basically? Resolution is the ability to see two close by points as separate. That is a key thing. Okay, we want to be able to, in principle, if you want to see at the atomic scale, you want to see two atoms as separate entities. Magnification is not quite the same as resolution. I want to make this point very clear, right? I know that this contains atoms and I can see it. I can see the atoms because these comprise of atoms, right? But in this, I cannot see two atoms that are next to each other as separate entities. What we really want a microscope or something to do is to basically resolve or see those things as separate. Magnification alone is not enough. So please understand this difference between resolution and magnification. Any optical instrument, whatever it might be, from the simplest one, our eye is also, you can think of it as an optical instrument, the simplest hand lens to very simple light microscope. Any of these optical instruments, the biggest problem is the so-called diffraction limitation, as it is called. What happens is that if you take a point and the object and you have the optical system, it forms an image, let us say. Unfortunately, what happens is that a point in your object is not mapped onto a point in your image. If a point is mapped onto a point, then there's no problem. The point actually gets spread out. So then what happens when you have two very close by points, you have two spread out things, they start overlapping. Therefore, we're not able to resolve the thing. That is the whole problem with any optical system. Any optical system that contains any of these lenses and apertures have this so-called diffraction limitation. In high school or even before that, we studied, right? Bending of light around obstacles. It goes to where the geometric shadow is and so on. It doesn't restrict itself to where the aperture or the slit is. It actually bends beyond. This is what we call as diffraction. This is true for any system. Okay, so this is the first limitation that we have. Any optical system will have this diffraction limitation, and therefore that is why it's not possible. So then what can we do? Obviously what we can do is to make to see what the width of that thing depends upon, how much it is spreading. And if you make it as narrow as possible, then we can improve our resolution. That is the whole idea. So then the question is, what are the factors that basically affect how wide that thing is, right? So here, you can see, okay. The pointer, okay, doesn't matter. So we want to make it as narrow as possible. So it turns out that when we have these two of these peaks and they're far apart, we can actually resolve them. So that is the minimum resolution that we can get. But once they start coming closer to each other, they start overlapping, and this particular situation where we're not resolving it. Okay, so we want to make it as narrow. So the point is that width of that peak basically depends upon only two things. Depends upon the wavelength of the light that we're using, and depends upon the size or the dimensions of the lens or the aperture that we're using. Basically, according to this equation, the so-called Rayleigh criterion, it says that we make d, the diameter, as large as possible, which means the width will become narrower and narrower, or we make lambda, the wavelength, as small as possible. Okay, so it turns out that if we make the simple solution seems to be we can use this visible light, but make d larger and larger. That will give you better resolution, right? In principle, it will give you better resolution. But what happens when you make d and d larger? For any lens, the other possible problem is that as you make this d larger and larger, rays that are coming further away from the optic axis, they are not going to focus at the same time. This is called spherical aberration. Because the lenses have spherical surfaces, they don't get focused at the same point. So by making d larger, we are not gaining anything. What we are gaining over the diffraction limitation, we are losing for spherical aberration. Therefore, increasing d is not a real practical solution for improving the resolution. The only other possibility is to change lambda itself. Lambda for visible light, of course, is of the order of half a micron, roughly 500 nanometers or so. And therefore, the resolution that we can get in an optical microscope, the width of the peak that you get, gives you a resolution roughly of the order of a micron or slightly better than that. Okay, so we want to make lambda very, very small so that we can improve the resolution. And how do we do that? We do that by basically using electrons. Okay, we make use of the de Broglie relationship, the particle wave duality that we have. And when we accelerate electrons across a potential difference so that it gains a velocity v, there's a de Broglie wavelength associated with it. Lambda is equals h over mv. Okay, by changing the velocity, that is the accelerating voltage as it is called, we can change the velocity, and therefore we can change the lambda. Typical values of lambda that we use in the microscope, electron microscope, this is what we have. We can see that for 200 kilovolts, if we use an accelerating voltage of 200 kilovolts, we can accelerate electrons almost to 2/3 the velocity of light, very, very high speed electrons. And these electrons typically have a wavelength of the order of 0.025 angstroms. Compare this with about 5,000 angstroms that we have for visible light, which means that we should get much, much, much better resolution than what we have in a visible light. So that is a basic idea. By using lambda that's much smaller, hopefully we can get a much higher resolution. But that's only one part of the story. It turns out that the lenses that we use in the electron microscope, whatever they are, obviously they're not glass lenses. They're basically electromagnetic lenses. Unfortunately, the quality of these electromagnetic lenses is much, much poorer than the glass lenses even that we have in terms of spherical aberration. They're extremely poor lenses. Okay, and therefore, even though we have a lambda which is very, very small, it is not possible to get resolution that's comparable to this. Unlike in visible light, where 0.5 micron roughly gave you about a micron of resolution, we get nowhere near 0.025 angstroms. Okay, the state of the art currently is is roughly of the order of 0.5 angstroms or so. Okay, that's still very good, extremely good, but the problem is because the lenses are very, very bad. So that is the key point. And so one of the points that I want to make is that all of us, many of you are wearing glasses because for spherical aberration basically. So if I remove this, whole thing looks like a blur to me, right? And suddenly wear this, everything becomes bright again. So what is happening, right? Because things are getting blurred, this is the situation that we have here. Things are not getting focused at the same point. But once you have a diverging lens, the glass that we have here, it actually acts in the opposite way to our eye, and therefore we can get actually again point convergence. This is how we actually correct for spherical aberration. Unfortunately, it turns out that there are no diverging lenses for electrons, the way it works. Due to lack of time, I am not going to tell you everything, but at least I'll point you, and if somebody is interested, I can explain that later. Okay, so there are no diverging lenses. Therefore, people have actually come up with very, very detailed, sort of complicated sort of methodology to come up with corrections for aberration for the electron microscope. And the modern generation of microscope, this actually happened only the late 90s or so. The first set of aberration correctors happened, and that is why now it's possible to have subatomic, sub-angstrom, not subatomic, sub-angstrom resolution in the electron microscope that enables us to see things that was absolutely not possible to see before. Okay, and that is absolutely critical and important for characterizing and understanding materials and nanostructures in particular. Okay, so typically, so 75 years after this famous talk of Feynman, now we are at a situation basically where we have the so-called aberration correctors, which basically are correcting for the spherical aberration of your lenses that you have. Therefore, we can actually do really lots of fun things. And the people basically associated with that, these are the 4 gentlemen associated with that, Harald Rose, Maximilian Haider, Knut Urban, and Andre Krevanek. Okay, so it's only a question of time before the group of 3 among these will basically get the Nobel Prize, I think. Okay, so what is the transmission electron microscope? I just gave you the overview of what the electron microscope is doing. Now, although we talk of TEM, a transmission electron microscope, as one technique, it actually comes in many forms, shapes, sizes, colors even, right? So there are many different kinds of electron microscopes, each capable of doing a few things. When we talk TEM, typically it's almost like 25 to 30 different techniques rolled into one. It's very powerful. I'll tell you what are the things that we can do, and these are the kinds of things that we can actually do. This is a 1 volt, 1.25 million volt electron microscope, which means that you're actually accelerating electrons to very high energies. Okay, and that's basically used for electron for damage of materials and so on. There are multiple things. These are the modern generation microscopes. The current state of the art microscopes, I'm just giving you 2 examples. There are others from Geo also, for example. These are the aberration corrected microscopes. I will give you several examples from what we can actually get. Okay, the way I'm going to do this particular talk is not going to talk about the the physics and how the electron microscope works in details, but rather what I will do is I'll show you examples of what we can actually, the information we get from nanostructures, and in showing these examples, I'll briefly explain how you basically get those and what is the analysis that we can do. Because I think if I start going into the basics, it's going to take a very long time, and I teach this course for the whole semester, right? And so it's very difficult to compress it in one hour. So rather than that, I'll give examples. Hopefully you can relate to some of these examples from your own work, and then you will probably gain something. Okay. So what then can the TM do? I told you it's multiple techniques, right? It can do what's called as imaging, which is obviously straightforward, that we can look at things at a much higher resolution. So that is the first thing that a TM is expected to do. It can do diffraction. All of you, I'm sure most of you heard of X-ray diffraction, Bragg's law and X-ray diffraction, things like that, right? We can actually use electron waves to get diffraction from materials. So, and that's a very good thing because we can get crystallographic information. The third thing basically we can do is chemical analysis. One of the things that your electrons basically does is that when it falls on the material, it actually knocks off inner electrons, which means that electrons from the outer orbit will just come down. I'm using very loosely, which means that the difference in energy will be emitted as X-ray photon. These X-ray photons have characteristic energies depending on what the delta E is, right? And therefore, you can use them to find out what elements are present in the material. This is your EDS or X-ray analysis that you have in the TM. Okay, by analyzing the X-rays that are coming out from the material, when the electron impinges on them, you can characterize what are the elements, EDAX as it is called. EDAX, by the way, is the name of a company. Okay, EDS is the technique. Okay, so EDS basically we can do to find out what the elements are. And there's another thing, spectroscopy. The electrons, when they go in, they actually can transfer energy to the material, and therefore what comes out actually has lower energy as compared to what is going in. Suppose something is going in as 200 kV, it comes out as slightly lower energy. So these energy loss, these are actually characteristic of the various inelastic process that can happen in a material. So this is very similar to what you can get in X-ray photoelectron spectroscopy. We get peaks, for example, 284 point something for carbon and so on. You can get these characteristic peaks of energy loss. When you see a peak at 284, it tells you that carbon is present in a sample because electrons have lost that much energy in causing that kind of an excitation. Okay. Similarly, we can get this energy loss spectroscopy, yields as it is called. Okay. There are individual techniques that are actually better than the TM for each of these things, possibly. Okay, we can do imaging, STM can give you atomic resolution. X-ray diffraction is still the gold standard because electron diffraction can never beat X-ray diffraction in terms of the the accuracy and the third or fourth decimal place that you can get for your lattice parameters and so on. Chemical analysis, there are much better techniques which can do things at the ppm level maybe, and XPS of course is great, right? But what actually gives TM the edge is that you can get all this information from the same small region in the specimen, often approaching atomic dimensions. That is not possible with any other technique. The spatial resolution is what basically sets the TM apart from all other techniques, and you can get all of this from the same instrument, same sample, same region. Okay, that is the power of the TM. Of course, then why everybody should be doing TM and nothing else, right? It's not really like that, because TM also has its own problems and other associated things. Please remember, particularly for the students, it's never technique A versus technique B. It's always technique A and technique B, because each one technique has its own advantages, disadvantages, strengths and weaknesses, and depending upon the information that you want to look at, sometimes even a simple visible light or optical microscope is good enough. You don't have to go to an electron microscope if it gives you the information that you're looking for. Okay, so please choose a technique based on the information of the science that you're trying to do, what information that you're trying to get from the specimen. Okay, so the problem with the TM, okay, interpretation is not straightforward, right? So this is a photograph of a two-headed rhino that was actually discovered somewhere in Africa, right? And you know the rest of the story, right? There are no two-headed rhinos. What you're essentially seeing here is something in projection, two rhinos standing one behind another. And in projection, it looks like a two-headed rhino, right? TM, you always see things in projection. When you have two things that are one on top of another, and you look at it in projection, it looks as if they're touching each other. You know, they're overlapping. You understand the problem? So projection can give you serious problems if you don't, and you can misinterpret things. There may be no boundary between them. You can say, oh, there's a very nice boundary between these two phases, but they may be miles apart. I mean, they may be quite, spatially, they may not be even in contact with each other. So we should be careful. Poor sampling. Other very, very important thing. Typically, you make a 3 millimeter specimen, a very, very small specimen, and you're looking at a 1 micron by 1 micron, even much smaller, 10 nanometer by 10 nanometer region. And you're making big stories about what your material contains. Okay. So the analogy that I often give is that you're trying to conclude about the forest by looking at the fine structure of a leaf. Okay, so you cannot do that, right? So you need to be representative. You have to look at multiple specimens, many different regions. Only then you can say about what your specimen contains. You cannot just look at one region, found something interesting. Okay, let me write, so anyway, so you should be very careful about the representative part. And the third and most biggest problem is high energy electrons will damage your specimen. There's no getting away from that. Any specimen will get damaged by electron beam. Doesn't matter what specimen, right? If you keep electron beam long enough on the specimen, it will get damaged. Biological specimens, polymers and other things will get damaged much more faster. All other inorganic specimens also will get damaged. So it's very important, right? Therefore, one of the golden rules is that whenever you see a good region, the microscope move that region away from the electron beam. Suppose, then you can do all your alignments, other things, and then just before you want to image, only bring that region so that you can do your recording and so on, right? So don't expose the electron beam more than necessary. That's another simple and most important rule that you always follow, right? So the point is that in spite of all these advantages, you have significant number of disadvantages also. So you have to keep that in mind, okay? So what happens? These are the kinds of things. We have a thin electron specimen. Obviously, the two important things, characters that are important. This is called transmission electron microscopy, right? Which means that electrons are transmitting or passing through the specimen. The two requirements. The specimen has to be thin. Unless the specimen is thin, the electrons will not transmit. For nanomaterials, that's not a problem because you already have dimensions of the order of nano. Therefore, typically most nanomaterials, particles and so on don't require any serious sample preparation. But if you're looking at bulk materials, nano-grained materials, then you have to make them sufficiently thin so that electrons can pass through. And typical thickness is of the order of 100 nanometers, depends on various things. The second important thing is that the electrons have to have high energy, so that they have energy to transmit or pass through the specimen. Okay, so these are two requirements for the TM rather, and therefore you can have all these kinds of interactions. It turns out that when you have high energy electrons falling in a very thin specimen, most of the electrons, 90% of the electrons just go through without interaction at all. Only a very small percentage of electrons interact. And these interactions basically can be of two types, or they can be, you can describe these interactions in terms of many different classifications. The simplest one you already heard about, elastic and inelastic scattering, right? The elastic scattering is one where the electrons pass through without any change in energy. Okay, So those are the important ones for which, like Bragg diffraction and other things. You have the same wavelength, same energy, you just they undergo diffraction, and therefore you can actually get electron diffraction patterns and so on. Coherent and incoherent. Okay, when you talk of elastic, inelastic, they are using the particle nature of the electron, right? Whether the particle is losing energy or not losing energy. Coherent versus incoherent, we are looking at the wave nature of the electron, whether the electron wave is scattering in phase or out of phase, or they're scattering randomly. So the coherent is scattering. Forward and back scattering, whether the electron that's coming in is back scattered or forward scattering. For the TM, when you have a thin specimen, high energy electrons, mostly it's forward scattering, and kinematic and dynamical scattering. Okay, whether the electron is scattering only once, a few times, or scattering multiple times in the specimen before it's going through. So all these things become important. I'm not going to talk about the detail, but keep in mind that these are all becomes important in interpreting your images and diffraction patterns and other things. These are the things to keep in mind. Okay. So let me briefly tell you about the TM in 2 minutes, about imaging and diffraction patterns. For that, I'll just take an example of, for a simple analogy, so that it actually makes sense. Suppose I have a glass sheet and I have painted some regions black, and I have light, parallel beam of light that's actually falling on it, and I have a screen or detector below. Okay, suppose initially that there's nothing, it's a plain glass. What intensity will I see on the screen? Uniform intensity, there's no change at all. But once I've painted some regions black, what will happen? Light will not pass through those regions, and those regions you will basically see the shadow of those regions. Light is not passing through, therefore you will see either bright and dark regions depending upon what you have. Exactly same thing happens in the TM. You have a thin specimen, parallel beam of electrons falls on the specimen. If the specimen actually scatters electrons away, scattering the electrons away, direct electrons will not go through. Those regions will appear dark because the electrons are gone away from the direct path. Okay. On the other hand, so on this scattering can be many things. This scattering can be diffraction, it can be whatever other forms of scattering. Anything that takes the electrons away from the direct path, that region will appear dark. So if you only collect the direct beam that's going through, whatever is coming in the same direction, if you put an aperture, what you get is what's called a bright field image. You must have heard of bright field images, right? The bright field image is where you use a direct beam to form these images. What you could do is that instead of using putting an aperture to collect the direct beam, you can put an aperture to collect the scattered beams. So then what will happen? When I put an aperture to collect the scattered beams, only those whatever regions are scattering, they will appear bright, because only from there those electrons are coming. So these are like sort of complementary. Whatever is bright in a dark field image will be dark in a bright field image, and so on. So this is a simplest form of contrast in the TM called as amplitude contrast. Okay. Parallel beam of electrons falling on the specimen, two things happen. Whatever is going in the same direction after passing through goes in different directions. Okay. This is the simplest form of the scattering, which is coherent forward elastic scattering. It's called as diffraction, exactly similar to what happens in X-ray diffraction. 2d sin theta equal to n lambda. The only difference is that d is same because the material is same, for example. Lambda, what can we say of lambda? I showed you lambda for X-rays, typically 1.5 angstroms or whatever, copper K alpha, 1.54 whatever, right? Electrons, what did we see lambda? 0.025 angstroms. Your lambda is so very small. What is the typical 2 theta values for X-rays? Few tens of degrees, right? You get 10 degrees, 20 degrees, 30 degrees, something. Because lambda is so small here, from the Bragg's equation, Bragg's law, you can get that the theta will be really, really small. Theta will be much smaller than a degree. All your backscattering, every peak that you see in your X-ray diffraction, everything will be compressed to less than a degree. Very, very small angle scattering that you will have. Okay. So whatever is going in one direction, after it passes through the specimen, it will go in some specific direction. This is called Bragg diffraction. This is your angular intensity variation when a parallel beam falls on the specimen. This is what we call as a diffraction pattern. We can use lenses to focus each of these different beams to form spots. That is what we see as a diffraction pattern on the screen. Okay, so this is what you see as electron diffraction patterns, right? You see multiple spots. It means that you have the beams are actually going in different directions. They basically use a lens to focus them onto different points. Each point in their electron diffraction pattern refers to a beam going in different directions. Exactly the same Bragg angle, at the same Bragg angles correspond to the lambda that we have. And because of this angular intensity variation, different regions of the specimen may actually scatter or diffract differently. And therefore, like I told you, dark and black and white, right? So different regions, you get a spatial intensity variation. Some regions will appear dark, some regions will appear bright. This spatial intensity variation is what we call as an image. So a parallel beam falling on the specimen, if there is no specimen, uniform intensity. Once you put a crystalline specimen, two things happen. The angular intensity variation, which is called as a diffraction pattern. There are other ways also of scattering, but the primary means is the diffraction pattern, and the spatial intensity variation, that's called as a image basically. Okay, this is what is the basis of what is called as your amplitude contrast images, because we are seeing differences in amplitude of the beam as it passes through the specimen. Okay, this is one thing. Okay, so in electron microscope, everything is to do with the angle of scattering. If you are able to characterize how the electron scatters at all possible angles from 0 to whatever angle, the angles are not very, very large, as I told you, fairly small angles. 2 degrees, 3 degrees is a very, very large angle for electrons. Okay, then we know completely everything about our material. We can go back and say how the scatterers are present in real space, and therefore we can actually get information from the specimen. Okay, electron diffraction or diffraction itself is a huge field in itself, and I don't have the time, unfortunately, to talk about the physics of diffraction, but I hope all of you have encountered X-ray diffraction and things like that. So the physics is very, very similar, but the details are quite different. Okay, so I will leave it at that. Okay, for those of you who are interested, so they had this, wrote this article several years back actually, but it basically captures different things in your, what happens in electron microscope and how you can actually use it to investigate nanostructures. If you're interested, you can actually go through this. Fine. Okay. So now let me actually come back to, I told you about this diffraction, let me just come back to the actual ray diagrams. How does a TM work? As I told you, we have a parallel beam falling on the specimen. On the right hand side, what is basically shown is a specimen from specimen down. We have parallel beam falling on the specimen, and we saw, I told you that electrons go in different directions, the Bragg angles. Use a lens to focus them to form the diffraction pattern. Okay, suppose now you want to form a bright field image, I only have to select the direct beam to form the image, so I have to put an aperture there. Or if I wanted to form a dark field image, I put an aperture to select only the diffracted beam. These are bright field, dark field images. There is yet another mode that which we can use, which is called as phase contrast imaging. In phase contrast imaging, what we essentially do is that instead of selecting only the direct beam or the diffracted beam, I put a larger aperture and select more than one beam or multiple beams at the same time. And then what I will see below is basically interference pattern corresponding to these different beams. And what you have seen, or what you commonly see as high resolution images, right, lattice fringes and things like that in the transmission electron microscope, is nothing but an interference pattern. All you're seeing, you're not really seeing the atomic planes edge on or whatever, right? The high resolution or phase contrast images is basically an interference pattern arising because of the interference of the multiple spots that you have in your electron diffraction pattern. That is the basis for phase contrast. Okay, so this is the primary modes that you have in your transmission electron microscope. There is yet another important difference here. So far what I have told you is what happens in a conventional TM mode, as it is called, where we have a parallel beam falling on the specimen. Okay, and then we have this angular intensity variation and so on. The second mode that is very common nowadays is to use what is called the scanning transmission electron microscope mode, STEM mode. Here, instead of using a parallel beam, we use a finely focused beam. Okay, and that basically scanning on the sample surface. If you have encountered scanning electron microscopy, the idea is very, very similar, that we have a very fine probe that actually scans on the sample surface and we get the information. But the big difference is that we don't have a bulk specimen, we have a thin specimen, and all the imaging happens below. Okay, so the STEM mode has become very, very popular because the aberration correction in particular that I told you, it is now possible to get probes that are sub-angstrom or angstrom size probes, and that can scan on the sample surface and get information point by point. Now if you have a specimen that is suitably oriented, crystalline specimen that is suitably oriented, we can have atomic columns. We can actually look at individual atomic columns in a specimen. We can, just like Chandrabhash showed you that schematic, right? We can see atom, we can actually see individual atomic. I'll show you several examples. Okay, the STEM mode has become particularly popular because we are now able to see, even in the high resolution phase contrast, we can see high resolution. But in the STEM mode, we can directly see interpretation is much more straightforward. Okay, so I will show you the so aberration correction. I'll just show you. If you want to get phase contrast or other kinds of images, you should correct for the aberrations in so-called objective lens. If you want to do it in the STEM mode, we want to correct for aberrations in the condenser lens. That's called the probe corrected TM. And if you have enough money, you can get a double corrected microscope that's able to do correction in both these lenses, and we can get good high quality phase contrast images as well as STEM images. Okay, we have one such probe corrected microscope at IISc. That, by the way, that's actually a national. I will talk to you a little bit about the facility at the very end. It's a national facility, and if you are interested in accessing and using that, of course, it's on a chargeable basis. All of us have to pay for that. It's a fairly nominal charges for students and educational institutes in particular. You can get in touch. You can look at the website AFMM at IISc, and then you can get in touch with one of us to see if what can be done. Okay. What I'm going to do now on is to not talk about specific details of the physics, but I'm going to show you several examples of what the electron microscope can do. Okay. So who is keeping time? Can you just tell me when I have about 5 minutes left? Who's keeping the time? Anyway. Yeah, so just tell me when I have about 5 minutes, whoever is keeping the time. Okay. Fine. So let me show you different examples from with things. Some of it is from our own work. This is not, the purpose is not to talk about specific material systems or what about the work, the material system per se, but rather about what the microscope can do. That's what I want to show you basically, right? So this is an example of, this is among the first papers, by the way, which actually used aberration correction in the transmission electron microscope. Now what you can actually seeing, right? The top right, what you're seeing is a bilayer of graphene. Below, you can see beautiful hexagonal. You're actually seeing individual carbon atoms. It's not a picture hand drawn or anything. It's actual carbon atoms that you're seeing. And on top, the top layer that you can see, that is a bilayer. There's another layer sitting on that. The current microscopes can actually see things at this particular level. Individual defects in graphene or any two of these 2D materials or whatever materials, we can actually see directly. That is the power of this thing. So this is among the first papers, Zia and Orman's papers, among the first papers that used an aberration correction, that paper that's published in Science. Using STEM mode, this is something called boron nitride, and we have defects of carbon and sodium and so on, right? Again, this is nature. All around similar time, slightly later than that possibly, right? Where you use a STEM mode to look at individual layers of boron nitride and show where carbon atoms are sitting, where nitrogen atoms are sitting. Okay, one point I just want to make, I'll talk briefly about the STEM and then what information it can give us. Okay, I will just skip these things and then, okay. So now I want to show you, I'm going to show you several examples with the scanning transmission electron microscope. So I will tell you what is the principle and how we can actually, what is that we are actually seeing in terms of atom, right? Suppose we have specimen, this is an example of a specimen, silicon specimen, which contains one red atom there, which is, or few red atom there, which is antimony. The main difference between these two is that these have very different atomic number. Electrons are basically scattered by the nucleus and screened by the outer electron that you have, which means that heavier atoms will scatter electrons more. Therefore, when we collect the electrons that are scattered to large angles, by large angles I mean about 2.5 degrees, heavier atoms will actually would have scattered more. Those regions will appear brighter because they have scattered more. That is the basic principle. And suppose I have very, very fine probe that I can locate on individual atomic columns. I can tell you which atomic column has higher atomic average atomic number and which column has lower average atomic number. Okay, I'll show you this example. We have a fine probe here. I will run this animation. We have a fine probe that's falling on the specimen. Okay, and then we have it's passing through the specimen. It gets scattered by the specimen, and then what we're going to have are basically detectors to collect the angle, the thing that is scattered to large angles. This technique is called high angle annular dark field imaging. It sounds complicated, but if you break it up, it's very, very simple. High angle because you're collecting things at large angles. Annular because the detector is like a donut, annulus. Dark field because it's dark field, you're not looking at the direct beam. It's called HADF. So when you scan the electron beam, whenever it actually passes a column that contains a higher atomic number thing, that column is going to appear brighter. What you're seeing as individual columns of silicon in this particular case, and whatever is appearing brighter here tells you that either the number of silicon atoms is more, or you have something that's heavier that's sitting there. That's what this essentially means. So now this gives you a very direct interpretation of what your specimen contains. This is among the first examples of the use of STEM for your atomic level detection. So it can actually do multiple things. Okay, so I will just skip this thing. So this is what actually the image looks like. From Bell Labs in 2002, they actually showed that the white dots that you have on the right hand side, you don't see any of those white dots, pure silicon. Once you introduce antimony in these things, the bright dots are basically antimony atoms that are sitting inside the columns. When you have larger, appears brighter, it means that there may be more than one atom, 2 atoms, 3 atoms, 4 atoms, or whatever it is. So you can clearly see that at atomic resolution, you can actually see what is actually sitting at the individual atomic columns. So that is the power of the modern day electron microscope. Another example, this is from the Antwerp group, and we have a multi-layer structure, thin film multi-layer structure. We're looking at it in cross section, and you can clearly see that the bottom layer, your intensity is appearing brighter. Central layer is slightly lower. Again, the top layer is different. Basically, this one layer, this is lanthanum, strontium, manganese oxide, and strontium titanate, multi-layer structures. The atomic numbers of each of these things are different. You can clearly see that which is the higher atomic number region, which is higher atomic number column, which is the medium atomic number column, and low atomic number column. You can actually distinguish between those things in a suitably oriented specimen. So this is directly, we can visualize atomic level things inside a thin film material or a nanostructure. We can do similar sort of things for nanoparticles or whatever it is, right? You can actually look at the intensities from individual. I'll show you examples from nanoparticles also as we go along. This is another example, again same sort of same thing from a single platinum nanoparticle. One single platinum nanoparticle which shows all these beautiful facets. At the center of the particle you get higher intensity because it's thicker in the center and you see much more intensity, and as it goes towards the edge you can see how it actually terminates at the steps and so on. This is a very, very beautiful, one of the earliest images that shows a single platinum nanoparticle at atomic resolution. Okay. I'll show you some of the images that from our microscope that we have. This is a monolayer structure of your MOS2. Okay, so this is the kind of thing that we are able to get at our thing. So in this particular case, I should tell you that you're only seeing the higher atomic number. You don't see MOS2, right? You're not seeing the lower atomic number element. You are only seeing molybdenum in this particular case, because only molybdenum actually scatters electrons. There is a way to look at the lower atomic number scattering. If you put an aperture at lower angles, at lower angles, you get more scattering from your sulfur, and you can actually also see that. Okay. So this is a thing, and tungsten oxide. See, each of these things, it almost looks like it's drawn by hand, right? Each of these dots. What you're seeing is atomic columns. This is a tungsten oxide material, and more interestingly, you can look at some kind of defects. You can see all these linear defects in this thing, right? You can actually characterize them. What you are basically seeing here, you can see a discontinuity here in these atoms. That is what is basically called as a crystallographic shear structure. Okay. Once we have this kind of an image, on the right hand side is shown what is the pure tungsten oxide structure. You can overlay on that. When we heat this tungsten oxide in a reducing condition, what happens? Oxygen goes away. And oxygen goes away only along specific planes. So if you remove specific planes of oxygen, the yellow dots that I'm showing there, and then we have octahedra, tungsten oxide octahedra that have only, instead of 6 coordination, they have only lower coordination. Therefore, the whole structure shears, so that they can actually, instead of corner shearing, they become edge shearing. Never mind the details, but you can actually see those details directly in the electron microscope. That is basically what is shown as a crystallographic shear structure. Okay, so that is the power of the modern day microscope. The octahedra that are corner sharing at the boundary, they become edge sharing. Okay, so I'll skip this particular thing. Okay. So one of the important things about nanostructures, right, and why it becomes important, why such microscopy becomes important. All of you know that when you make things into nanomaterials in nanoscale, these number of atoms, the surface becomes significant fraction, right? Typically 70%, 80%, 90% of the atoms reside in the surface. Surface atoms obviously have lower coordination. They're not surrounded by all atoms all around, which means that the structure is not the most stable structure, right? Therefore, atoms can move or relax to to form a lower energy structure. Okay, what I'm going to show you the next example is we actually make ultra thin gold nanowires in our lab. Ultra thin nanowires means these are about 2 nanometers of diameter gold, single crystalline gold nanowires, extremely thin. They're 5 to 6 atoms thick. And gold, we know that is phase-centered cubic. We know where all the atoms should be sitting and so on. But because the significant number of atoms are sitting on the surface, what essentially happens in this case is that the atoms actually move around. significantly compared to your equilibrium FCC positions. And we can actually see that displacement. These displacements are of the order of picometers, tens of picometers. You can see such displacements in the electron microscope. Okay, this is an example from our own work, where we have these ultra thin gold nanowires, and what you'll actually see, this is the wire growing along that particular direction. These are the 111 planes in the gold nanowire. Okay, and what I'm going to show you, never mind the details, what I'm going to show you is that the atoms actually, instead of being planar, are now formed like a ripple. They form wrinkles, and you can actually directly measure those wrinkles using the electron microscope. Again, this is the example of where the microscope directly comes to the aid of understanding nanostructured materials. Why this is important? Every single property that you think you knew about gold changes once we go to this length scale. Okay, it's no longer a good metal that you thought it is. It becomes sort of semiconducting / insulating. It becomes catalytically very active. All kinds of bizarre things start happening for gold in this particular scale. And all those things can be explained by understanding how the electronic structure changes because of the relaxations and so on. Okay, so that is one thing that, that can be done. Fine, so there is another example of this one. Okay. How about multi-component systems? Again, this is an extension of what I told you. When you have different elements that you have in a material, can we find out where the elements are sitting? Okay. For this example, I'm going to take an example of an alloy nanowire. Alloy nanowire meaning a gold and palladium both present in a nanowire, and we want to see where gold is sitting, where palladium is sitting, whether they're mixed uniformly and where they're sitting, right? It turns out that palladium is much lower atomic number as compared to gold, and therefore in your HALDF images, the atomic columns of palladium are going to look less brighter because the atomic number is lower, right? And so I'll just show you without going into the detail, these are different alloy nanowires that we've been making in our lab. I'll just show you that this example, right? Can you see the image to the right? At the center, you can see a brighter region. Okay, and the corner, the outside, you can see a shell sort of thing which is lower, less brightness. This, what we are forming here is basically a core shell nanowire. A core which is comprised of higher atomic number gold, a shell, very, very thin shell, 2-3 atomic atom thickness of shell that is essentially forming of a lower atomic number palladium in this particular case. We form a core shell structure, which again possible by, we can do all the hypotheses and all the other things, but directly seeing gives you the proof, right? Property will change, everything will change, and you can hypothesize that this thing might be happening. But with the use of the electron microscope, we can directly see these things happening. So that is the power of the modern day electron microscope. Okay, how much time do I have? 10 more minutes, okay, good. Fine, so we can actually do the atomic mapping. Anyway, so, okay. The next example that I want to give you is that I talked about spectroscopy, electron energy loss spectroscopy, right? So far I showed you imaging, structure and composition. Now I will show you what you can do in terms of oxidation states, right? I told you your electron energy loss spectroscopy is very similar to XPS, right? Where you can get oxidation states and things like that, right? Imagine we can get a fine probe, we can locate an individual atomic columns, and we can get your electron energy loss spectra, and we can actually map out the oxidation state. I'm going to show you an example of strontium titanate, which is highly reduced. Normal strontium titanate, strontium is in +2, titanium is in +4, oxygen obviously 2-. Therefore, it's simple. But when you heat it under reducing conditions, titanium actually can go to lower oxidation state. And we want to map where these titanium ions, how are they reduced and where they're sitting basically. Okay, and for this again we use a model system of strontium titanate nanocubes that we actually make in the lab, and we are heating it in a highly reducing atmosphere. And we want to ask the question, how is this titanium is reduced, what oxidation state is it present in, and where is this actually present in the material. Okay. The details are there. I think the slides are going to be shared with you possibly, so you can actually have a look at that later. So, and of course, as it gets reduced, it becomes darker grayish in color. It absorbs light over a wide range, implications for properties and so on. Never mind the details. Again, we use STEM mode. Okay. Using imaging, you can see that what you're seeing here is a cube. You're looking along the edge. The top to surface, you can see that the top two layers are very different from what is contained in the bulk. That is the first indication that something is happening on the surface. For the structural level, something is happening on the surface. But again, as I told you, this is a high angle angular dark field imaging technique, which means that you're only seeing the higher atomic number, you're not seeing oxygens. So you can use the complementary technique which is called as angular bright field image, and that clearly tells you that the lower one, that we have a TiO layer forming on the surface. The top two layers in this particular, the lower image here, right? This is a titanium oxygen layer. and structurally we are able to see that we form a layer of the titanium oxide in these highly reduced cubes. But can we actually get spectroscopic proof to show that it's actually TiO, where Ti is present in the +2 oxidation state? We can do that by doing electron energy loss spectroscopy. It turns out that Ti4 plus, depending on the transition that you have, will give you 4 peaks, whereas Ti2 plus will only give you these 2 peaks in energy loss spectrum. Therefore, when you have a fine probe and scan on the sample surface, you can actually see that at the surface, the interior of your cube, we basically get essentially 4 peaks corresponding to Ti4 plus. But as the probe moves closer to the surface or the periphery, we start getting evidence for Ti2 plus. We can map out oxidation states, we can map out structure, chemistry, and oxidation states using the modern day electron microscope. Okay, so this is spectrum, and as can show from surface to the interior how the 2 peaks becoming 4 peaks as we go there. And if you want to represent it in terms of a map, the red region basically tells you where your Ti2 plus is, and the green region is essentially Ti4 plus. But one small point I want to make here, right? Remember, we are seeing things in projection, which means that even if the top surface there is Ti2 plus, because top and bottom surface will have, but the contribution of that is very, very small. Therefore, actually there is red in the central region also, because you're seeing things in projection. That's a very, very important thing to keep in mind. But at the periphery, you only have that. That's why you're only seeing the red region at the periphery like you have here. Okay, so this is one important thing. Fine. Okay, so coming back to this problem of this projection problem, right? If you have a projection, then is it possible to get 3-dimensional information from a material, right? Ideal situation is that we want to characterize things in 3D, not only in the projected 2-dimensional image. Is it possible to get information in 3 dimensions? And how can we do it? Under certain techniques, there are 2 different techniques that we can actually do. One is the same information that I told you using your HADF images, right? Remember, I told you that more scattering, something will appear brighter. More scattering means higher average atomic number or more number of atoms. 10 atoms will scatter more than 5 atoms will scatter more than 3 atoms. Therefore, if some column is if a column is more intense or appearing brighter, it means that the number of atoms in that column also could be more. So if you have a single component system, which means there's only one element that is present, and if something is appearing brighter, it means that the number of atoms along that particular column is more. Therefore, when you get a HADF image, I'll show you the example from the gold nanowire, which I briefly talked about, and we see differences in intensity of different columns. We can reconstruct complete 3-dimensional structure of a single nanowire from a single HADF image, because we know how the intensity is varying for different things, and we know the structure. Okay, so this is the example that I'm showing you. First thing, this is the single nanowire. We can see that FCC gold nanowire, we can see different intensities for different columns. Okay, using statistical analysis, we can actually find out what are the number of atoms in that given column. Okay, the numbers I think are too small, unfortunately you cannot read it. The dark brown means 8 atoms in the column, slightly less thing means 7, and so on. So we can actually map out the number of atoms in every individual column for a single component system. Once you do that, and we know that the FCC structure, we can actually completely reconstruct the 3D structure of a wire from a single image. Okay, of course, these are assuming certain things and so on. So this is done in collaboration with the Antwerp group a few years back. Similar things, I'm not going to show this example of platinum also. So, okay, the other, how much time? 5 minutes? Okay, so the last 2 examples that I will give you is to do with actual tomography. Instead of actually doing from a single image, if you have multi-component system, what we can do is that we can actually tilt and get a tilt series and then reconstruct, just like you do it in tomography, right? CAT scan and whatever it may be. You can actually tilt the image at different tilts and then use all this information together, put them together to completely get a 3-dimensional information. So that thing also can be done. But again, the point, as you can see, is that projection images. This is a tortoise or a rabbit that's standing on its head, and it looks like a hand in projection. Therefore, it's very important to know 3-dimensional information. In projection, things can be very, very misleading, right? So the tomography essentially means you're getting it slices and putting all the slices together to form the whole apple in this particular case. Okay. I'll just show you one example or 2 examples without going into the details. This is an example of where we had this again done in collaboration with the Antwerp group several years back. This is an example of we had gold nanoparticles sitting on silica, and we are getting some kind of interesting and bizarre sort of descriptions, bizarre sort of results, which I'm not going to talk in detail about. It turns out that in this particular case, the gold actually was diffusing inside, and it was actually forming things inside. And you can actually see that in your tomography. diagram which basically shows a complete reconstruction of what the particle looks like. And using only tomography, we could actually show that gold particles are sitting inside, are going diffuse inside the hollow SiO2 shell. Another example where this is actually also of some lead telluride particles that are actually forming on tellurium nanowires and so on. Again, we can, unfortunately, this movie is not playing last when I saw it, but I'm showing you this is a three-dimensional reconstruction of such a heterostructure in this particular case, showing you where the individual components are present. Okay. Okay. So one last example maybe, then I will stop. So one of the problems, as I told you, hard-F images are great because they work for higher atomic number elements. But for lower atomic number elements, I showed you ABF, annular bright field images can help you. But it turns out that very, very light elements, even those things are not possible. It's very difficult to get that information, right? So another technique that has been developed more recently is something called as IDPC. And without going to the detail, let me just briefly tell you. We have an electron beam which is a charged particle, and we have an atomic column. When it comes close to the atomic column, it will get deflected. Therefore, the center of mass, if you just form a probe from that, the center of mass of that thing will actually supposed to shift closer to the atomic columns. In this technique, what we essentially do is to measure how the center of mass of this, from the diffraction pattern as it is called, shifts. And when we map that whole thing together across the specimen, it can basically, and the center of mass is directly related to the potential, electrostatic potential that is present, which is basically due to your atoms that are there. And using this kind of a technique, we can even image hydrogen. Hydrogen is the lightest element. We can image the presence of hydrogen in materials. It's a very important problem in many, many different situations. The example that I showed you for strontium titanate, this is not hydrogen. The strontium titanate that I showed you, right? The angular dark field image only shows you strontium and titanium. It doesn't tell you oxygen because it's lower atomic number. Right-hand image, you can see that the smaller atoms, you can see the small dots in between the squares, right? That is oxygen. That you're able to see in IDPC because now what you're actually measuring is how your electron diffraction pattern itself is shifting, the center of mass is shifting, and using that even lighter atomic number elements actually can be seen. Okay, I will skip these things. I will just say that for nanostructure, for characterizing nanostructures, the TM is an indispensable tool nowadays because it can give you so much more information than, of course, we have to use different techniques for different kinds of characterization. But for spatial resolution, the TM still basically reigns supreme. Okay. The last slide that I want to show you is, which I briefly mentioned, is about the facility that we have at IISc, the Advanced Facility for Microscopy and Microanalysis. It is a national facility, user facility. If you are interested and if you have specific problems to look at, please get in touch with one of us. You can go to the website and have a look. And the microscopes are available particularly for students from other educational institutions. You can definitely come and avail. It's important to know what can be done and what cannot be done. You can discuss with one of the local persons and see if the problem can be done. Then you can get in touch with me or anybody else at the center. Okay, I'll stop now. Thank you for your attention.
Suppose we want to observe real time,
right?
What's happening in the core of the sun, the dynamic thermonuclear fusion reaction.
Right.
We want to observe exactly what's happening inside the core of the sun. So, is it possible? What are the challenges in terms of technology available? And
in this case, it's not. First of all, the kind of temperatures that you have there, what we can do in these things are materials, thin materials that we can put inside the microscope.
I can understand the limitations of this.
Yes, yes.
Apart from this, what other technology available in the world? Not.
I'm not an expert in those things, so I think you're better off asking somebody else about that. So a thermonuclear thing, what happens? I'm not very sure what would be the best technique for that kind of a thing. At those kinds of temperatures, which is like several 10 power several degrees, I don't know what level of characterization can be done. So it's not an easy problem.
Okay. In another one, resolution is identifying two separate object sets, two different objects.
Yes, yes.
But at what distance? Supposing we are not able to see top of the Himalayas, why we are not able to see the top of the Mount
Absolutely,
Everest?
very good point. That is why if I have two dots, if I have it here, I may be able to see them. But if it's very far away, I cannot see it. That is why we talk about resolution. That's why instead of So instead of talking of resolution in terms of distance, we talk in terms of the angle subtended. The angle subtended is same. So if it's far away, the angle subtended becomes smaller. So we say what is the minimum angle that our eye can see. So now the distance goes away. It is that distance divided by this distance, right? So we don't talk in terms of what distance we want to keep it, but rather what the angle subtended, what is the smallest angle that we can see. That is why if you see the expression that I had for Rayleigh criteria, it was theta, not d. Theta basically contains both this distance as well as actually the spacing. It contains both those parameters, right?
Yeah.
Yes.
Hello. I'm audible? It's here.
Sorry.
Hello.
Yes, so most of the contrast thing that I talked about was for crystalline materials. There is lots of studies on looking at short range order, medium range order in glasses. There are groups in the world that are actually exclusively working on that. But if you have nanoparticles sitting in an amorphous substrate, those can be characterized. Those are crystalline particles, means you can actually get diffraction pattern from them, you can get structural information, all those things can be done. The only limitation, remember, is how stable your specimen is under the electron beam. If you're able to form a thin specimen, if it's stable under the electron beam, that kind of samples can be looked at.
So you have shown that silicon, if it is doped with antimony or heavy metal, so that the spot wherever we get, it will be little bit dark or broader. So similarly, whether we are going to get the image for this glass doped with
If the nanoparticles have average, for example, lead, I'm just giving an example, if they have lead rich, for example, right, they will appear much darker or brighter in your HUD image because their average atomic number is larger. That is simple sort of contrast that you can get. But remember, all those things required the crystalline specimen to be oriented properly. We have to see individual atomic columns, right? And therefore, for an amorphous specimen, it's not possible to do that. But at a lower resolution, if you want to see this region has average atomic number which is higher, the particles, for example, then those things can be done at a much lower resolution.
Yeah, you have mentioned that multi-layer analysis can be done. It's here.
Sorry, I can't
Yeah,
see you.
you can
Okay.
Yeah. The
Yes.
multi-layer analysis can be done.
Yes.
Like heterostructures or whatever. My question is like how many layers it's possible to do the analysis, maximum I would say, using HRTM, and how much accurate it's going to be.
Okay, so how many layers you form a multi-layer, many
Yes,
structures.
yes.
See, remember, when you want to see a multi-layer structure, you want to see it in cross-section. You can't look at it in plan view, right? Plan view, so all the layers will be one on top of another. You want to look at cross-section. So one of the biggest challenges in multi-layer structures is to actually prepare the specimen. You want to make them thin. Laterally, there's no serious limitation. If you're able to if you want to prepare a specimen, even microns we can actually see. There's no limitation on the number of, really there's no specific limitation on the number of layers that you can see. It can be even several tens, several hundreds even, depending upon what the lateral dimensions are. Microns, even 10 microns, if you're able to get a uniformly thin specimen, we are able to see it. The thickness now is not, we are actually making perpendicular to the layers. It has to be thin. You understand, you're making cross-section specimen. So the challenge is to actually make a thin specimen, basically cutting the specimen, right? If you can think of it like a multi-layer cake, right? You're basically slicing, making a thin slice and then looking at it along the other edge, right? So, but the sample preparation is a limitation. There are techniques to do that, but you should ensure that your sample preparation itself doesn't damage your specimen, doesn't change your specimen and so on, but it's possible to do.
So what are the complications with magnetic samples?
That's a good question, important question. Remember, your specimen is sitting within the objective lens, magnetic field of the objective lens. If it is strongly magnetic and it's not strongly bound to your holder, it can go and stick to the lens. Your objective lens is gone because the field will now get distorted, and later everything that you do will be a problem. Therefore, that is a big problem. There are field-free modes or Lorentz modes, as people call them, where we basically switch off the objective lens so that it's not sitting inside a strong magnetic field. We use other lenses to form the images. Resolution will go down, but it's possible to do that. The other foolproof way to do it is to embed, if you are talking of particles, embed your things inside a resin or something so that they are held together and then put them, then you can look into them. But again, those also will mask your features a little bit, but it's possible to do that. Free particles sitting on a grid, not a good idea. Yes. Right? by default TM, when you have 2D material, it's always forming with the whatever, basal plane or whatever it is, right, along that thing, and you're looking perpendicular to that. So the advantage, okay, I'm not sure I understood your question properly. The advantage with the TM, the diffraction in particular, not for 2D, generally is that we can actually tilt and then get diffraction patterns along different orientations. For 2D material, the question doesn't arise because it's a single, for example, single layer or few layers with a specific orientation that's actually, it forms face flat, always. Right? They're only looking along that particular orientation. So in 2D, there's always this specific orientation, right? There's no other way the sample can fall on the.
Sometimes the crystallites will tend to orient to a particular direction.
Okay, so in that case, we can actually tilt. You're not only looking at one specific thing, we can actually tilt your specimen to orient it appropriately. Even for a polycrystalline material, normally when you put things inside the microscope, they're at random orientation. We can tilt it along the axis, or this way both two axes of tilt are available, so that you can orient it along certain crystallographic direction. That can be done.
Sir, we generally see microscope like a vertical mode. Is there any instrument in the horizontal?
Good question. The first instruments are actually the horizontal mode, right? Of course, gravity doesn't have any role to play in this one. So, but the point is that first actually instruments were actually shooting electrons towards the user. But now then the conventional design is to actually only form vertical microscopes. Various design issues are there, but all current microscopes are all, but the very first microscopes that are actually built were actually horizontal. Okay.
So further questions can also be taken offline. So we'll be around for a while. Please put your hands together to thank Professor Ravishankar N for giving this insightful talk. And may I request Professor Ravi Kumar kindly to do the honors. Thank you, sir. So ladies and gentlemen, that is the wrap of the morning session. Lunch is being served at Kalinga 2. So you will have to go out of this premises, find the GBR, that's the Great Ballroom, and exit through that, the ballroom to find Kalinga 2. Yes? So we reassemble around 2 to 10 latest, 2 o'clock, yes. So we'll reassemble at 2 o'clock to continue with the